Okay, welcome back, everybody. It's good to see you. I didn't scare too many away your first day. All right. Okay, just a quick note before I continue. Concerning assignments. Now, uh, as I mentioned, the homework, you have two attempts for the homeworks. There's no time limit. The activities also have no time limit, but there's one attempt. Now, if there's something that you have to submit in the activities and for some reason it didn't come across or you forgot to submit it or something, you can still submit it, okay? I mean, go ahead and submit it. You can go back into the activity, resubmit. That's no problem. I will accept that. If Canvas is acting up and it's not allowing you to resubmit an activity, try it in the comments of the activity, see if that works. Then if that doesn't work, go to Canvas email and just attach it to the Canvas email. And then finally, if that doesn't work, send it through my EDU email, okay? So multiple options. These are for items that you need to upload. Like you have the activity, for example, the welcome activity, and throughout the activities, you'll have something similar. You got to turn something in, submit something. So, all right. Any questions about that? Okay, everybody know where your stuff's at. Everything's set up in modules. You can get to your textbook, assignments, and no surprises, right? Okay. Okay. A quick reminder also, my Friday is my class with SEC. You're more than welcome to, log in. It's from 1 o'clock. Check, yeah, 1 o'clock to 4:30. They meet one day a week, whereas you guys meet twice a week. So, and I'm going over the same material. Okay. All right, so let us continue. We were on chapter 1, slide number 9. We're beginning to talk about the physical states of matter, and I showed you here how we depict them with diagrams, where the one on the left is the solid. You can see here that the circles there represent molecules, compounds. Everybody's, fairly structured, ordered. That indicates a solid material. The next phase, obviously, is the liquid. Again, the molecules are still close together, but they're not as rigid as a solid. They're flowing, moving around. So that diagram would represent a liquid. And then the gas, again, the same circles representing molecules or compounds, whatever. Quite a big distance between them. They're totally separated. There's a lot of gap between them, a lot of compressibility. And so that would demonstrate, these diagrams will depict all the three different states of matter. And what we're doing when we're going from, let's say, from a solid to a liquid, see these molecules, whatever it may be, are interacting with each other. And that interaction is a force. And some of these forces are very strong, and it takes a lot of energy to break those forces apart. And so when we take a piece of ice, which is in the solid form, and then we put energy into the system, what we're doing is we're breaking up that force that's holding them together. This is what we call IMF. We're going to have a whole chapter on that called intermolecular forces. Some molecules have strong IMF forces, some have weak, which then affects the properties. So when we put energy into the system, we're breaking up that interaction, causing these molecules or compounds to break apart and stop interacting with each other as strongly, whereas they go into the liquid phase, where they're still together, but not as strongly as in the solid. And if you continue to add more energy into the system, that liquid, eventually you'll break those molecules apart as far as the interaction. Now, you're not breaking up the molecules, okay? That's important. You're not breaking up the actual structure of the compound. You're breaking up the interaction between the molecules. Okay, totally different thing, breaking up the molecules within the compound itself. All right, so one of the properties, we talk about the properties of solids. Solids have a fixed shape and a fixed volume. Okay. And I'm sure you're well familiar with that. We got a fixed shape and a fixed volume. And even though they're in the solid phase, back this demonstrating the solid phase, matter doesn't just sit there. They are vibrating. Sometimes because in the solid form, they are vibrating kind of not so much as compared to, say, in the liquid, but they're still vibrating even in the solid form. Okay. It's not till we get to like absolute zero where it's theoretically thought that all matter stopped, everything stopped, even the vibration within the molecule. We haven't attained that temperature yet. Come close, we're not down there yet. Okay, so that's what we mean by vibrating. A lot of them are in crystalline shape, very ordered, and even though they're solid, they could be still have solid properties, but they're not as ordered as a crystal would be. They're not compressible, very little compressibility, because you can see it by common sense tells you, right? The molecules are very close to each other. There's no room. They can't come in together. And the other thing to think about now, because we have the model here, this represents some type of molecule, okay, and they're real close to each other. And on the outside of these compounds are electrons. Okay, we're gonna talk a lot about the structure of the atom. There's electrons around all of them, and electrons have a negative charge, and negative charges repel. And so not only are they, it's kind of like what you call a dichotomy. Two things happening here. One, they're attracted to each other for a variety of reasons and stick together, but at the same time, they're also repelling each other because on the outside, it's just loaded with electrons that have a negative charge. It's analogous to two magnets where you have the north and north, they repel each other, okay? And so it's fascinating when you think down in the atomic scale that whenever you grab something, because in the fingertips, your fingers on the surface are electrons too, you're really not really holding on to the object. They're kind of like, there's a space between them, because the electrons are repelling each other. Okay. So, and then we introduced this property, which we call density. Kind of introduced it a little bit early. It is nothing more than, it's an equation, but it's a ratio, okay? It's a ratio of mass over volume. All matter has density, because all matter has mass, okay? We can measure its mass. Now, we use the term weight and mass interchangeably. There is a difference between mass and weight. But since we're stuck here on Earth, and the difference between mass and weight is related to the gravitational forces on Earth. Okay, because we all know, or maybe you don't, but your weight on the moon is quite different than your weight on the Earth. I kind of like the weight on the moon because you're a little bit lighter, right? However, your mass is the same, regardless if you're on the moon or on the Earth. So, and there's a difference, but because we are on the Earth, we tend to interchange the term mass and weight. So you can think of mass and weight as one and the same, but keeping in the back of your mind that they're really technically, as they say, different. So anyway, the ratio of mass over volume, everything has a mass and everything has a volume, okay? So if we can measure the mass and if we can measure a volume, we have what's called the density. And normally density is the units that we have for density is grams over milliliters. We'll get into the units more. So milliliters. That's generally the most common units for density. Okay, it's a ratio. Now, given any ratio, which is where we're going to talk a lot about the next two chapters, is any ratio that we're going to work with, I can write them one of two ways. I can write it as grams over milliliters, or I can write it as milliliters over grams. And how I set that up depends on the units and depends on what I'm going to do with that factor. Now, grams over milliliters, no different than if you're working, you have a rate, your pay rate, dollars over hours, right? Okay, when you're traveling on a car and you're, within the speed limit, right? You got miles per hour. That's a ratio. And every ratio that I want to talk about here, we can invert. Keep that in mind, okay? Because a lot of these problems that we're going to do calculations, we're going to keep track of the units. And by keeping track of the units, you should not have any problem. So anyway, so most solids have a higher density, okay? Very high, a high density, independent solid. And compared to their material, if that material was in the liquid state, okay? For whatever piece of matter we're talking about. The only exception is ice. Ice has a unique property, okay? That, for example, water, if I take 1 gram of water, and I measure its volume, guess what? At 25 degrees at room temperature, its volume would be 1 milliliter. Okay, 1 gram of water will have a volume of 1 milliliter, which means that the density of H2O will be equal to 1 gram per milliliter. Okay. And we use that as a reference point. So that means that anything with a higher density, higher than 1, would tend to sink in water. A rock has a higher density than 1. And when you throw it in water, here's what's going to happen. It's going to sink. Okay. A lot of things have a density that are less than 1. And when things have a density less than 1, float. Now, why does water float? Why does ice cubes float? Okay. Now, if I take that 1 gram of water and I freeze it, guess what? For ice, its new volume is no longer 1. In fact, water increases when it freezes. So its new density, which was initially one gram, which is the same weight, but its new volume is, it could be about 1.1 milliliters. Because it's increased. That's a unique property about water. But now they do the division on that ratio. And guess what? Ice has a density of about 0.9 grams per milliliter. It is still H2O. It's still water. But because in the solid form and because it expanded when it became solid, it has a new density. And that is why now ice cubes float. Okay, because the density of ice is much less than 1. Okay. All right. Very unique for water. That's a unique property. In most other things, that doesn't happen. All right. So solids, because they're locked in position, then they're not going to diffuse, they're not going to ooze out, and mix with anything else. So they're locked in position. So they tend not to mix very well. With respect to liquids, okay, liquids take the shape of their container. Right? Think about this. You got a gallon of milk, 2-liter bottle, whatever. And it has a particular, and I fill a 2-liter bottle of soda pop. It has a particular shape of a soda pop, 2-liter bottle. And I take that 2 liters and I dump it into a 55-gallon drum. Its shape is changed now. I still have the same volume, 2 liters, but it has a new shape because it takes the shape of the container. So liquids take the shape of the container and they have a constant volume. Okay. Different liquids flow at different rates. And that's simply because, again, that IMF I just talked about, that interaction between the molecules, certain liquids tend to want to float, are not as viscous. Water in a race of flowing, just say not floating, but flowing, the race of water versus honey, water would win. Okay, because water is less viscous than, say, honey, or even motor oil. And that has to do with the viscosity, and it has to do with the forces of the molecules with each other. Okay, these IMF interactions. They're not compressible, because just like solids, the molecules themselves are close to each other. There's not a lot of room in there, so they won't compress. which is a good thing because with liquids, specifically say oil, we can use that to use, without that property, we wouldn't have power steering. You wouldn't have power brakes. I don't know if you ever driven a vehicle with no power steering or used power brakes. It's pretty tough. But with the fact that we have hydraulics, it allows us to have, power steering, power brakes and things like that because of the non-compressibility of the liquids. Their densities tend to be much higher than gases. Gases are the least dense, followed by kind of liquids in the middle, and then solids are the most dense. Now, when the liquids are miscible, means that they dissolve in each other, they will mix uniformly. A classic example would be, let's say, a mixed drink. You got alcohol and water, right? You mix it here, it dissolves, then you get a whole mixture. But what happens when you have Italian dressing? Anybody know what happens? If you have two layers in Italian dressing, you have an oil layer and an aqueous layer. They do not mix very well because of the properties of the oil and the water, which we will talk at length about. All right, now gases, they take the shape of the container like liquid. They literally have no shape, okay? Not only that, they can compress and expand because there's so much space between the molecules. We know that the volume increases as the atoms get further apart, right? Think about this way. If you take a balloon, okay, and just kind of blow it up a little bit, not all the way, maybe halfway, tie it up, and then get a hair dryer and start heating that balloon. You can try this at home. You can see that balloon is going to expand. And why would it expand? Because you didn't add any more air into the balloon. All you did was heated it up, and that balloon starts to expand because there's more energy into the system, causing the molecules, the gas molecules, don't want to separate. Now, if you take that same balloon and stick it in the freezer, guess what's going to happen? It's going to shrink because those gas molecules in the freezer now loses energy and they start to come together a little bit better, okay? And start to interact with each other, so the volume decreases. All right, so the point about the volume is this: for gases at this point in time for this class, gases have no volume. We're going to learn down the road that only under specific conditions, very specific conditions, that gases will have a specific volume. But as it stands right now, no set volume, okay? They tend to have low densities. An example, air around us has a density, look at that ratio, 0.001 grams per milliliter, much less than water, 1 gram per mil. Okay, gases tend to intermix with no problem. Our air around us tends to be a mixture of 78% nitrogen, okay, and 21% O2 and carbon dioxide, and a series of bunch of other gases out there. Notice the subscript. Let me introduce that real quick here. Notice I put N for nitrogen, then I put a subscript in the bottom. What that tells you is that there are two nitrogens bonded together. We would normally, and I'm going to discuss this at length, we would put a nitrogen and then stick a bond, specifically 3 bonds. And each line represents a bond. Don't worry about, we're going to talk at length about bonds, but those 3 lines represent a bond. Now, instead of having to write it like this all the time, we simply put N and then the 2 subscript to tell us that there's 2 nitrogens bonded together, just like there's 2 oxygens. We tend to call these are elements, but they're diatomic, okay? And they're di meaning 2 and atomic meaning 2 atoms put together. So we're going to find that there's 7 of the elements that are diatomic. By themselves, under these conditions, they're not very stable. They cannot they cannot survive. So what they do is they combine with another atom of the same species to form a diatomic element, which makes them stable. Okay. All right. Kind of briefly introduce a little bit about that, because then we throw in these subscripts and we don't really start to explain, you know, what does that mean? Got two in there. Now, that is different. Heads up. That is much different than putting the subscript versus a coefficient. All right, like this. Okay. That subscript, when you see a subscript, and we're going to learn how you're going to determine what that subscript can be. Once that subscript is set, it's etched in stone. That never changes. And that is necessary for that molecule. When we put a number in front, like a 2, that's a coefficient. We can change that number anytime, the big coefficient, we can change it any number of times or any value. But that subscript doesn't change. Okay. All right. Gases exert pressure, okay, to hit the sides of the container. Don't believe me? Go measure your tire pressure in your car. Hopefully it's about 32 psi, right? And if you have a leak, what happens? The tire pressure drops. Where do you go? You go to Circle K, Quick Trip, you get some air, put in your tire, pressure goes back up. You put more mass into the tire, and you got more molecules in there, banging up against the wall, and pressure goes up. Okay. All right. So in essence, to summarize the solid, liquid, and gas, solids have a fixed shape and they have a fixed volume. Okay. Liquids do not. Liquids follow the shape of the container, whatever they may have, but they do have a fixed volume. And gases do not have a fixed shape like liquids. They have the shape of the container, and they do not have a fixed shape. Okay, at this point, they will down the road, but only under specific conditions. All right, let's talk about physical and chemical properties. Okay, when we talk about physical properties, we're talking about properties of the chemical and some information or facts about the chemical, such like color. You know, what color is that chemical? Is it colorless? Is it blue, green, brown, yellow, whatever it may be? A lot of chemicals have an odor. Okay, some of them are very nice smelling. If you like wintergreen, for example, you know, the mints, those are chemicals. I'm going to ruin your food and your treats, because I'm gonna show you, hey, look at the chemical you're ingesting. Because we don't think about it when we're ingesting food, but when you really think about it, we're ingesting chemicals. So anyway, the wintergreen is a chemical, and the way they make it is you take an organic acid and then alcohol, and you put them together, and separately they don't smell too good, but you put them together, you make a new type of compound called an ester, and they smell pretty good. Things like wintergreen, things like banana oil. These are chemicals that are ethical. Anyway, then again, some chemicals smell bad. If you have natural gas at home, they spike it with a little bit of a sulfur-based compound. And that sulfur-based compound is very foul smelling. And the reason they do that is in case there's a gas leak, because gas itself is odorless. So you spike it with a little bit of nasty smelling, very little amount of sulfur-based compound, so you can smell it. You know, you ever got hit by a skunk, you got hit by a lot of sulfur-based compounds. All right, so paste, which I don't recommend, you know, if you're working in a lab, but obviously the foods that you eat are chemicals, so you taste them. The texture, the melting point, that is the temperature when they start to go from, say, solid to liquid. Okay. The physical state, which we denote by the letters S, lowercase s, L, and G, solid, liquid, or gas. Density, which we talked about. These are all physical properties, whether it's soluble in water or whether it's soluble in oil. Okay. Whether it can conduct electricity. And whether, what kind of hardness, is it real brittle material? Or is it, hard as a rock, like diamonds? Okay, diamonds are extremely hard. Chemical properties are things like how they react, how they behave under certain conditions. Are they explosive? Like TNT, dynamite, trinityltoluene, that's what TNT is. Very explosive. You got to be careful handling it. Is it corrosive? Does it react with other metals to destroy them? Is it toxic? Is it poisonous? Or it could be inert. Pure gold, for example, is inert. It is so inert, we call it the noble gas because it doesn't, the noble metal because it does not react. If gold that was buried a million years ago is still as shiny as it is at the moment you unearth it, because it hasn't reacted very much or as much with the environment. Okay, so these are the type of chemical properties. Okay. Now, when we talk about physical changes, the thing to take away from this part is that the structure, the chemical structure of a compound going from one physical change to the other does not change. That's important here, okay? If we take water, for example, and we freeze it, we have ice, solid water, right? We heat it up, it goes to liquid. It is still water, H2O. And if we continue to heat it up, it goes to steam and vapor, and it's still H2O. Those are physical changes. Okay, so that's what we're talking about here. Physical changes. The chemical structure does not change at all, going from one to the other. So when we have a solid going to a liquid, that's melting. Okay, solid going to a liquid. When you have a liquid going to a gas, I think you all know this one here. You should maybe, because you're boiling. If you're boiling water, you're getting liquid going to a gas. We call that boiling. It could be called evaporation, okay? Or it could be called vaporizing. Now, think about this for a second. We all know if I put a pot of water on the kitchen top to boil some water, that as I turn it on, eventually the water, if I leave it alone and I forget about it, I come back, the pot is empty because all the water got boiled away, right? We all seen that or have it done. I've done that a few times. But why is it that if you take a cup of water and you leave it on your kitchen table and you come back maybe a week or two, and maybe you start off with a couple milliliters of water and you come back, it's totally gone. Okay. Where did it go? How come we understand how we're heating it on the stove, but this cup is just sitting on the bench top. We're not doing anything to it. But it evaporated, all that liquid evaporated. Okay, I'm sure you've seen that, right? All that water evaporated. Why did it evaporate? Is there something magical? Some Harry Potter stuff going on? No. Okay, that's a demonstration. That's a demonstration that the water molecules are moving when they're sitting there in the cup, sitting on your bench. They're moving around to each other, and the guys in the center, they're bouncing back and forth. I don't know. You can see how they select the Powerball number. You got all these balls bouncing around. As it take the number you were seeing in, or you play bingo and you see the balls, the bingo numbers inside a container, bouncing around in the container. Well, these things are doing that. And some of them on the surface get enough energy to get out of the liquid stage and go up into the vapor phase. With time, all of them go into the vapor phase and don't require any external energy. Okay. And just a demonstration that molecules are always moving. Anyway, going from a gas to liquid, condensation. All right. So here I got a couple of soda pop, Diet Coke. Okay, it's full of ice. And on the outside, I got moisture. Now, where did this magical water come from? Did it diffuse from my cup inside my cup outside? No. where did this water that's on the outside of my container, where did it come from? Some Harry Potter magical stuff here, right? Yeah. I mean, you've seen it, right? If you're at home, go get an ice and cup of water and a cup of ice cold water or glass, and then let it sit there, and the outside it starts to get liquid. And if it's humid day today, it gets liquid pretty quick, right? So where did that magical water come from? Any ideas? It's condensation. Okay. From the air, exactly, Samantha. All around us, we have humidity. We got, this Arizona used to be a lot drier than it is now. We got a lot of humidity, more so than it did, say, 50 years ago. So these air molecules are all around us. These air molecules are high energy. That's why they're far apart from each other. They come by, and just by chance, they hit the side of my container, which is cold. They lose some energy, okay? And losing some energy, the molecules start to attract each other again and condense and get attracted and go from the gas phase back to the liquid phase. And with time, you get a lot of moisture on the outside, okay? It's all about energy. So that's called condensation. Now, going from a liquid to a solid, obviously we call that freezing, right? So you get water, stick it in the freezer, you got ice cubes. This one you may not know, okay? This is where you have a solid material going to the gas, directly from solid to gas. Whether it goes, if it even stops at the liquid phase, it may, but it's just very quick, bypassing it. It goes directly from solid to gas. That's sublimation. A good example of this is dry ice. Now, does anybody know what dry ice is? Is it really H2O? Yeah. I know you can go to Fry's and buy some dry ice. Anybody know what that is? Dry ice is nothing more than carbon dioxide, which guess what? Is a gas. Okay. And so you can take carbon dioxide, gas, run it through a system and convert it to a solid. So you got a block of solid, which is carbon dioxide. And then because the environment's then, it's gonna want to go back from solid to gas. So that's what that little smoke is coming out. Okay. And what's really cool about this, if you want to help your plants out at home, go buy some dry ice and put it around your plants. Why would you do that? Don't put them on your plant, because dry ice is cold. You want to hurt your plants. But why would you put it around your plants? Any ideas? Or you can talk to your plants. Why would you do that? For psychological reasons? Well, that too, but that might help. Yeah. Helps me. I talk to them, a couple of plants here. But why would I talk to the plants? Or put dry ice near them? Energy? That's correct. Because carbon dioxide is a plant requirement, a plant food, if you will. Yes. And why would you talk to them? Because one of our products that we exit is carbon dioxide. So talking to the plants would aid them. They pay you back by what? Their product is oxygen. We need oxygen. They need carbon dioxide. So talk to your plants or give them some dry ice. All right. So now going from gas to solid, we call that deposition. So if we take carbon dioxide, here's a little special, it's very easy to do as far as making dry ice. You got a little special unit. You can take a carbon dioxide cartridge and just create dry ice very quickly. Anyway, going from gas to solid, we call that deposition. Okay, deposition. And going through all these stages is the matter of energy. I'll have a slide here, for example. Anyway, what I want to do is demonstrate, well, how do we show a physical change? But not only physical, we also show a chemical change. And we use the infamous reaction arrow right here. And so, you know, I could do this in general terms, say A plus B. Oh, come here, B. Here, my pen has been acting up. You do a C plus D. Okay. This arrow tells me there's a process occurring. That process could be either a chemical reaction or a physical process. Okay. To the left of the arrow is where we place the reactants. The reactants, and I apologize for my pen here, but it's reactants are to the left. So A and B are reactants. C and D are my products. I don't know, I'm gonna have to do some troubleshooting on my pen here. Okay, and that's how we present a process, chemical or physical. And so if we look at this process right here, and we're going to show you some reactions that you're going to look at. So I don't know what those chemicals are, and that's okay. What I want you to do is to analyze that process and look at the reaction, look at the structure. What we have here is H2O, okay? It's on the left side, so it is a reactant. And then on the right side, we have, guess what? H2O again. Nothing's changed. It's still the same formula, okay? Nothing's changed. So that is a flag to tell you, you know what? I underwent a physical change, okay? Because nothing happened to the formula. I did not break down H2O. For example, I could take H2O and have it undergo electrolysis, and I just put some energy through it, and I can break it up back to hydrogen gas and oxygen. That is a chemical reaction. That's why it's so important we find water out in space, because we can use oxygen to breathe for the astronauts, and then we can use hydrogen for fuel. Anyway, you notice here, I got water, I got my arrow, and then to my right in the reactant side, I got a plus. A plus should signal to you, oh, I got two products. That tells me I have a chemical reaction process, okay? We'll have some examples of that in a second. So then, since H2O remains the same on both sides, then I just look at the chemical state, physical state, and I can see that L is liquid and G is gas. So the only thing that happened here is a physical process, whereas H2O went from a liquid to a gas, okay? All right. And obviously we call that boiling. This is the whole process here, what we just talked about. It is a function of energy. It's a matter of putting energy into the system or taking energy out. Now, when we go from a solid to a liquid, we're putting energy. I'm going to designate that as E, energy slash heat, which is energy. We're putting energy, and we're doing it, we're breaking up that interaction between the molecules to keep them so that is ordered, and they go into the liquid phase. And if we continue to add energy to the system, more energy, guess what? It goes into the gas phase. Okay. Now, in the gas phase, we can take energy out, cool things down. And that's where the condensation, like on the outside, we got the water molecules out here in the atmosphere, and they hit my cold container on the outside. Energy is removed from them, okay, and they condense. The intermolecular forces take over, and they go into the gas phase. And if I continue to remove energy, that liquid goes back to the solid phase. Okay, so it's a function of energy back and forth, back and forth. The thing to remember about energy in Mother Nature is energy spontaneously goes downhill. So you go from a high energy state to a low energy state. We can reverse it, but you got to put energy into the system to reverse it. Okay, think of it as climbing a mountain. I got to climb that mountain. I got to put energy into that system, into me, so I can climb the mountain. Now, I'm on top of the mountain, I trip, I'm going to roll down with no problem whatsoever, get to the bottom, just boom, spontaneously hit the bottom of that hill. All right. So it's a function of energy going back and forth. All right. So as I stated, atoms are always moving, even in a solid state. Okay. And so when you heat a solid, in this case ice, the particles are gaining energy. That energy has a specific name. We call that kinetic energy. It's movement energy. It's like, all right, let's say you're out on the beach. It's a hot day, 100+ degrees. You got no shoes on. You want to go from point A to point B. And now you're going to walk across that hot sand nonchalant, or are you going to run? Because the sand is hot and you have no shoes. Of course, you're going to run, right? That energy is going to make you run. You're putting energy into the system. It's kinetic. It's movement energy. You're going to move faster. Okay. So if you have enough energy and you overcome these forces, you're going to cause that material to either go from a solid to a liquid and a liquid to a gas. Okay. And eventually, we have the diagram here to show very structured order to less structured order to basically disorder with respect to the molecules going from solid, liquid to gas. Now, with respect to chemical changes, here we are totally changing the structure of my reactant. Okay, something's going to happen to it. It's going to totally change. All right, we call these chemical reactions. So the starting material, the reactant, is completely destroyed and it creates a new material. Okay, here's my car. Yeah, right. Okay. All right, a good example would be a combustion reaction. Now, what you see here is a very generic formula. It's C subscript X, H subscript X. Let me highlight that here, right here. This is a generic formula for what's called a oh my goodness, come here. Hydrocarbon. Sorry, it's not working here. I'm going to hydrocarbon. Okay. The smallest hydrocarbon you have, where X for carbon is 1 and H is 4. So that's methane. That is the smallest hydrocarbon. The point being is this is an introduction to the first. I talked last Tuesday about the types of reactions. There's only 6 reactions. This is one of them. This is a combustion reaction. For anything to burn, okay, you require oxygen. So when you burn your vehicle, which consists of a variety of different hydrocarbons, these are compounds made up of nothing but carbon and hydrogen, okay, you need oxygen. Without oxygen, nothing's going to happen. Now, for Chem 130, the only 2 products that you make in burning a hydrocarbon is carbon dioxide and water. Yes, I realize that in your vehicle, in your exhaust, you are creating carbon monoxide. And that's simply because the inefficiency of your motor, of our motor, to burn the fuel efficiently and 100% efficiency. We're probably around 30–40%, I believe, efficient as far as burning our fuel. So a lot of we have a lot of wasted energy. Anyway, so we make only carbon dioxide and water. Okay, so those are the emissions. And if you ever see a vehicle in front of you and you look at the tailpipe and you see liquid coming out of the tailpipe, what you're seeing is that water coming out, okay? FYI. All right, so burning gasoline is an example of a chemical change. You have totally changed the reactants into new products. That carbon in a hydrocarbon used to be a hydrocarbon. Now it's in the form of carbon dioxide. It's still carbon, and that's important to remember. I still have carbon, but it's now in a different form, okay? So what kind of things indicate that there's a chemical reaction? Well, there's a multiple things, but some of the things that we'll present is this. Obviously, it's going to burn, okay? Burning wood, we got a burning chemical process going. It's not reversible. As far as I know, the only thing that's burnt that's reversed has been the phoenix bird. Okay, that's the only guy that's come back. Okay, so once you make the ashes, it's kind of tough to reverse it. Rusting is another thing. Rusting is a good indication. I used to have a truck where I had a lot of chemical reaction, and it was pretty rusty. All right, release of bubbles. Could be fizzing without any heat. A classic example of this is Alka-Seltzer. Okay, what do? You take Alka-Seltzer, you dump it in water, and you get fizzy. There's a chemical process. Now, I have a little pet peeve about Alka-Seltzer. Does anybody know what that bubbling action is by chance? When you take Alka-Seltzer, you dump it in water and fizzes on you. That is definitely Harry Potter stuff, right? Magically, you got bubbles. Well, where'd they come from? And do they have any medicinal value? Okay. Anybody know what's next time? Tell you what, next time you use Alka-Seltzer, read the ingredients. And you'll see that you're gonna find probably citric acid, okay, which is an organic acid, and you probably find some kind of bicarb in it, some sodium bicarb. Okay, now they're in the solid form, so they're in the pellet, and then you have a binder that binds the pellet together. Okay, holds everything together, and since they're in the solid phase, they're not going to react with each other. Now, the moment you dump it in the water, the binder breaks apart, releases all the chemicals, the active ingredients to help you with whatever your headache or whatever, but also releases the bicarb and releases the citric acid, which then those two react. Citric acid reacts with the bicarb to make carbon dioxide, and that's the bubbling. And that's what you get. You know, it's the same thing as if you make chocolate chip cookies. So most of the recipes call for baking soda. Any idea why you put baking soda in there? Because the recipe says so, right? Try making a cookie with no baking soda, a chocolate chip cookie. Do one batch with, one batch without. Okay. Or the other thing is try making bread, one with to help it rise. Exactly. There you go, Ellie. To help it rise because the baking soda and heat breaks down, forms carbon dioxide, and helps the cookie get rise. Otherwise, you get flat cookies. The same with bread. If you don't use, why do you put bugs in your bread when you make them? You're like, what do you mean bugs? I don't put bugs in my bread. How you do? You put yeast. Those are bugs. Yeast reacts with the carbohydrates to form one of the products is carbon dioxide. It's a plant. So carbon dioxide then causes your bread to rise. Without it, you get matzah. Anybody know what matzah is? Unleavened bread. Okay. All right. You know, I use food a lot as an example. There's a whole field in chemistry called food chemistry, because food is chemical processes. Cooking is a chemical process. It really is. You know, there's a whole group of scientists, their whole function. It's all they do is look at food and how to make food, how to store it, and what happens to give you a certain texture and so forth. Anyway, enough of that. Formation of solids. Sometimes you have two liquids. You put them together. They're clear liquids. You put them together, and boom, a precipitate falls. Okay. that is a precipitation reaction. It's one of the 6 reactions that we're going to deal with. Okay, so that's a good indication of a reaction proceeding. Or you can get, or you get heat. Heat is emitted. You go to CVS, you buy a hot pack or you buy a cold pack, right? I don't know if you ever done that. You go buy it because you hurt your muscles and you need a hot pack. You go, you buy it, you smack it, chemicals are released, process occurs, that pack gets hot. Put it on your muscle or wherever. Okay, that's a chemical reaction. Or the cold pack, same thing. You break it up, it gets cold. A chemical reaction proceeds. Okay. Or you can have these glow sticks. You know, what do you got to do? You got to crack them, right? And you hear that cracking. Inside is a little tube with a chemical, and outside the tube is another chemical. And then when you crack them, the chemicals get together, and one of the products you get is light. Light is emitted. Okay. Or I don't know, we don't no longer use flash cubes, but the old days for cameras, it was flash cubes, magnesium metal. When you burn it, it's very bright. Or there could be a change of color or even an odor, okay? There's an odor that you see, that's a good indication the reaction proceeds. Okay, now I'm going to show you a chemical reaction. It's probably one of the reasons that really got me going with chemistry, because this to me is mind-boggling. Okay, now I know we're new on here, but I'm going to explain it to you. We're new with chemical reactions and symbols and so forth. So let me break it down. Na is sodium. Okay, sodium metal, not sodium the type you put on your French fry. Okay, it's a different type of sodium. This sodium metal is just pure 100% sodium metal. It's a metal, it's metallic, it's very soft, it's extremely reactive. If I were to take that chunk of sodium, in fact, you can probably YouTube sodium metal and water and dump it in water, you get a very vigorous reaction and might even get an explosion, because it reacts violently with water to generate a lot of heat and hydrogen gas, which then the heat ignites the hydrogen, you get a big boom, okay? So you get sodium metal, it's an elemental form. This yellow material is chlorine, okay? Very poisonous gas. In fact, if you are around, if you're near a place where they have like a water treatment plant, and a lot of swimming pools, public swimming pools use chlorine to treat the water. They have tanks of chlorine. So if you're in there and you ever see a big cloud of yellow smoke, get upwind immediately, okay? Because what you're looking at is chlorine gas, which is not good for the lungs. All right, so you got a poisonous gas, chlorine, a totally reactive, very reactive metal. You put them together and you get something called sodium chloride, aka salt. This is what you can put on your French fries, okay? Which is not as hazardous unless you got high blood pressure, and that's a whole different story here, okay? All right, so, and the only thing that happened between here and here was a transfer of 2 tiny electrons. 2 electrons got transferred. These electrons are so tiny that we give it a mass of 0. They're so tiny, but they have a big effect. These are similar type of electrons that give you that bad hair day when your hair is like, you know, okay, and all that, and it totally changed the structure. Sodium chloride. All right, so that's a chemical reaction. So here we have a series of reactions. Okay, now granted, you're at the stage where you don't know what these things are, and that's okay. But you have powers of observation that I know all of you are here that have. You can analyze the reactants and the products, and the way they're written. If they look the same, then you know, boom, nothing's happened structurally, right? The first one is we have nitrogen bonded to 3 hydrogens. Okay, all right, so we got NH3. That's the reactants we got. Here's our arrow. That's our process. It's either going to be a chemical process or a reaction. So On the reactant side, we have NH3 and it's in the gas form. On the product side, guess what? It is still NH3, but then its physical state now becomes liquid. The fact that the formula did not change before and after tells you I have a physical change here. Okay. I'll come back and tell you what these guys are. You probably know what they are. If you have kids in dirty diapers, you know what this is, NH3. All right. Now, number 2, you got NH3 again. Okay. Then you look at the product side. God, look what happens. You get a plus. That should flag to you and say, I have 2 things at least, right? And sure enough, I do. I got something with 2 nitrogens and I got something with 2 hydrogens. Okay. And I totally changed the structure of NH3 to now I broke it apart back to its components. So this indicates to me I have a chemical change. Okay. All right. Look at number 3. At first glance, you might think that's water, but no, it's 2 hydrogens and 2 oxygens. And I'll tell you here in a bit what that is. If you ever cut your finger or dye your hair, you use some of this stuff. Okay. You look at the reactant side. Sure enough, I got another plus sign that again indicates I got products. I got at least 2 products, hydrogen and oxygen. But that indicates to me that H2O2 was broken apart again. So that would tell me I have a chemical process here. All right. Number 4. Here we go again with H2O2. I don't know what that is, but I look at the reactant side, it's still H2O2. Okay, so that indicates that it's still the same structure, so that is a physical process. Then number 5, the fact that I see nothing but carbon and hydrogen, guess what? Remember that general formula I showed you? Where it's CX, HX. Remember I called that a hydrocarbon? This was the general formula. But now we have a very specific example with X equals 6 for both the carbon and hydrogen. All right. So I look at the product side, that hasn't changed. So what does that indicate to me? It is still a physical process because I did not break that structure apart. Okay. So I got 3 physical processes and 2 chemical processes. Okay, so physical for the top one because nothing's happened to reactant or product. The reactant in number 2 got totally broken up into nitrogen and hydrogen. H2O2 also got broken up into hydrogen and oxygen in this case. So that's a chemical process. And number 4, it simply went from a liquid to a solid, which is just a physical change. Okay. And the same is true for number 5. Okay. All right. Well, let me tell you what NH3. Might as well get to know these guys because you're gonna meet them again down the road, especially this guy. This guy's ammonia. Okay, that's the formula for ammonia. And this one is the formula for hydrogen peroxide. Okay, I'm sure you've heard of hydrogen peroxide someplace. You've got cuts. I just read that they don't recommend treating cuts with hydrogen peroxide anymore. And I guess it does too much damage. I don't know, makes it matters worse. Kills the bugs in your fingers too. So, and then this is a hydrocarbon, specifically is a compound called benzene, which is not a good compound. It tends to cause cancers. Okay. All right, so let's talk about, we got about 15 minutes. Let's talk about the elements, all right? Now, elements are simply one type of atom only, okay? It could be a single atom, or it could be what I talked about earlier, a diatomic, like for example, hydrogen. Now, there are only 7 diatomics. We'll get to that here in a bit. There's 118 elements. Of those 118, only 7 of them are diatomic. And they're diatomic here on Earth because they're not stable by themselves. They need another molecule themselves to help stabilize. Okay. It doesn't mean that on the face of the earth, on the sun, that they could be in a different form, but here on Earth, they are diatomic. Okay, so the elements, we can't break them down any further. They are what they are at this point. If we break them down further, now we're breaking them down into the subatomic particle. And that's not, it's a whole thing called nuclear physics, and that's not what we're doing here. Okay. Compound. Now, how do we define a compound? Is anything that is comprised of 2 or more different elements. Okay. 2 or more different elements. I mentioned hydrogen gas earlier, H2, it's just 2 hydrogens. That's still an element. There's 2 of them, but it's still an element. But if I get my hydrogens and I bond them to oxygen, I get H2O, water. Okay, 2 or more different elements. That's a compound. Okay, the one we did earlier was sodium chloride. Okay. All right. 2 different elements. Then we talk about pure, obviously pretty self-explanatory. There's something that's, basically all by itself, nothing else involved with it. If something's pure, or we can have mixtures, obviously. Mixtures could be 2 or more different particles. They could be 2 or more different compounds with 2 or more different elements, or any combination thereof, elements and compounds. Okay, basically a mixture. Okay, so if we look at this flow chart here, we have matter. If we look at the mixtures on the right side over here, these spheres, different colors represent their single different colors. They represent elements. Okay, so we got, looks like we got 3 different elements. So we got a mixture of elements here on the right side. Now, if we look on the left side, we got 2 that are put together. That would indicate a diatomic element. Okay, so here we will have a mixture of a element and a diatomic, 2 different elements. One happens to be diatomic. Okay, with respect to compounds, we got to have at least 2 different elements. So sodium chloride could be represented by these 2 different color spheres. Okay, and then obviously this one here looks like Mickey Mouse here, Mickey Mouse ears. Okay, those are obviously the yellows are one element, and the red in the center is a different element. That is basically the way water is put together, where the red is the oxygen and the yellow represents the 2 hydrogens. And then in the far left here, pure elements, single elements all by itself, or diatomic. Okay, diatomic. All right. Now, examples of mixtures, all the metal alloys. Every metal out here is essentially a mixture. Very few things are pure. For example, even the rings that you may have, the gold rings, they're not pure gold, because pure gold by itself is very soft. It doesn't lend itself well to making jewelry. Good decorations, but in jewelry, they're very soft. So they mix it in with different elements, other metals, and to create something a lot more sturdy. So 18 karat, 24 karat gold are mixtures. Brass, for example, is a mixture of copper and zinc. And even stainless steel is not iron by itself. It's mixed up with any multiple of different elements. Some have carbon in it, and some other elements to make something that's strong. Okay, the air around this tap water, obviously, even if you got the only way to get pure water, you have to boil it and distill it. I should say, not boil it, but distill it. But tap water is loaded with all kinds of ions and so forth. The air around us also is a mixture. Things that are pure, if you make sodium chloride and you clean it up, it's nice and pure. Diamond, most diamonds have a little bit of impurity, but if you got a real pure diamond, guess what? It's made up of nothing but carbon. Think about this for a second. Diamonds are made up of nothing but carbon, okay? Also, graphite, which it has carbon and it's a dry lubricant made up of carbon, but it's very soft, very wet feeling, okay? And here we are, we got carbon and carbon. Well, why is it that diamonds are the strongest item on earth, whereas graphite are not? Okay, they're both made up of carbon. And the difference is the way the carbon atoms are put together relative to each other and these forces around it, these intermolecular forces. Diamonds are put in this position because of their structure, are very strong, the property of a diamond. We're all familiar with polystyrene, okay? We have polystyrene cups. Very weak, it crush them in your hand, no problem. They dissolve very readily in acetone or a nail polish remover. Put a polystyrene cup in some nail polish remover. It dissolves completely, very quickly. But if I can make polystyrene by playing with the reaction to make it, and it's made up of nothing but carbon and hydrogen, and make it so strong I can use it to build buildings. Okay, and the way I make them affects the interaction of the atoms with each other to give it strength. All right. Diagrams again to depict an element and a compound in a mixture. Okay. Which, by the way, for some of these activities, if you are gonna draw something, and it goes for anything. I mentioned if you you're taking your notes, if you write your notes, which was suggested to me by my boss like 50 years ago, he said write them in the manner that you can read them again a couple of years later and understand what you wrote. But the same is true for this. If you're going to write something and present it to me, look at it and say, can I read this again and understand what I wrote or a year from now, 2 years from now? Because I am getting certain ones that I look at and they're not marked. I don't know what I'm looking at. Okay, so mark your work. Show distinctly what you're trying to depict in your assignment. Okay. What we got here? Oh, getting close to 7 minutes. So we got diagrams up here. You can see that A is simply an element. Okay, that would be specifically a diatomic element, whereas B would represent a compound. Okay, we got three things bonded to a central atom of some sort. Now we're always going to tell you what the central atom is when we talk about structures. There's always going to be a central atom and then things will be bonded around it. Okay, so C again is a mixture of elements. That depicts two different elements. D is simply an element. There's nothing else in here. E definitely is a compound, okay, all by itself. And F definitely is a mixture, and it looks like a mixture of at least two compounds and a diatomic element. Okay. G again is a mixture of a compound and an element. And then finally, H is just simply an element. And if I needed to make a guess, H is a good representation for a solid element. All right. I was hoping to get a little bit further, but let me see. I got 5 minutes. All right. So let's briefly talk about the elements. Now, what I mean is this. If you're not done so, make sure that you print out the periodic table. And mine's marked up. Eventually, we'll talk about why it's marked up. But this periodic table, we're going to use quite a bit. Make reference. You're going to hopefully mark it up with all kinds of information. Okay. This periodic table also has a table on the left that deals with what we call polyatomic ions. I know it's all Greek right now, but it's going to make sense down the road here. We have this activity series that's going to allow you to predict whether certain types of reactions occur or not. And then we have a table here dealing with solubility rules that you're going to look at compounds and be able to determine whether that compound is soluble in an aqueous system or not. So if you haven't printed this out, do so. be familiar with it. The other one is the shapes. The shapes table has a lot of equations up on top that you can utilize. But more importantly than that, you have a table here that deals with the shapes. We're going to use this table. We're going to go through a series of steps to get to this table. And from this table, we're going to create a generic formula. And from that generic formula, be able to determine the geometry and the shape of that particular component. Okay, so these tables are quite important, and we do make reference to them quite a bit. So you haven't printed them out, make sure you got them for you. Now, each element, there's 118 elements. Each has a unique name, a unique symbol, and a unique number. Okay, now if we go back to that right here. Okay, so you can see all the elements here, 118. These down at the bottom row here, they've all been given names now. This periodic table hasn't been updated, but we have 118. In fact, the last, I want to say 114, 115, and I believe 117 were all discovered about 2 years ago. They've all been given names. And anyway, if you look at each element, they have a symbol, a letter. Whoa. Above the letter, there's a number, which is unique for that element. And then below that symbol is a atomic weight, okay, a decimal number. Okay, we're going to use all that information. So 118. So the first, when it comes to the symbol, some of them have single letters. But the point being is that single letter is always capitalized, okay? Some of the elements have a second letter, and that second letter is always lowercase. That's important because, for example, if I were to look, I was trying to describe or use cobalt, which has this symbol right here, capital C, lowercase o, and I inadvertently wrote capital O. What I described here is not cobalt, but what I described as carbon monoxide. Totally different, okay? So mind your P's and Q's. If you're looking for an element, that second letter has to be lowercase, okay? Unless you are talking about carbon monoxide. All right. Now, most of them have English names like H for hydrogen, O for oxygen, He for helium. A lot of them have their name derived from Latin. So PB is comes from plumbum, which means waterworks. AU, which is gold, okay, meaning golden dime. Be familiar with the first 20 with respect to their symbol and their name, okay, and where they're at on the periodic table. Where they're at in the periodic table is pretty straightforward. And I'm going to go through it, and then we'll call it a day here. So the first one, number 1, upper left here, is hydrogen. Okay. We go across the periodic table to He, which is helium. Li, second row, Li is lithium. Next to it is Be, beryllium. Number 5 is B for boron. Number 6 is C for carbon. Number 7 is nitrogen. Number 8 is oxygen. Number 9 is fluorine, not to be mistaken for fluoride, I-D-E. Totally different, okay? Totally different. Number 10, Ne for neon. Number 11, Na for sodium, okay? Number 12, Mg for magnesium. Number 13, good old L for aluminum, okay? Si for silicon. P for phosphorus. S for sulfur. Cl for, note the name here, chlorine. And as I said, fluorine, not ide, not chloride, but chlorine. And Ar for argon. Then finally, number 19 for potassium, okay? And not P, not for potassium. P is phosphorus, okay? potassium is K. And then finally Ca for calcium. Okay, and on top of that, be familiar with Ag for silver, Au for gold, Pb for lead, Br for bromine, I for iodine, and Hg for mercury. Okay. All right. I thought I can do a couple more, but I've gone a little bit over. And we'll continue on Tuesday with this chapter, and definitely we'll finish up chapter 2, and then chapter 3 we'll get done with that on Thursday, and then on the day of the exam, I do have lecture here. I do continue. You have the option. You can either, if you have questions, we can go over any questions about the previous chapters. But if there's no questions, I would just continue on with the chapters. Okay. So if you have any questions for during exam days, that's a good time to bring them. And one advantage of doing this is that at the end of the semester, we end up with maybe 1, maybe 2 days of what I call study days that I'm here, but we have no lecture because we covered up, we're ahead, we finished up the chapters way ahead. And those days are basically office hours if you want to come in with questions. Don't forget, if you do need tutoring, don't get tutoring. I am available between 3 and 4 by appointment. Let me know, and I can set up the Zoom, and I'll be there for any questions. If those times don't work, let me know. Maybe I can work out some other times for you. Okay. All right. Well, guys, have a good weekend. Have a safe weekend. I'll see you on Tuesday. Stay out of trouble.
Thank you.
Okay, thank you. Please. All right, guys, we'll see you. Thank you.
I did have a question, Professor Fred.
Yes. Go ahead.
It looked like it was a separate document, the periodic table that you had pulled out earlier with it had a key on it and everything.
Uh-huh.
That should be in our student resources, correct, in Canvas?
Yes, if you go to the very first module, it
Yeah.
should be there. It should have been up there where it says tables to print.
Oh, okay.
Okay, do you see it?
It should be under my syllabus as well, or?
No. It should be under the module of Canvas. Ruby Rose, hold on.
Oh, okay.
My little one threw my mouse away. Give me a second. I gotta get my
No
mouse.
problem.
Ruby Rose, what are you doing? She's like, that's enough. I want to play now. All right, let me call up here. Close this and okay. Let me share. Okay, I'm sharing the screen. And so if you
okay.
click under modules, okay, the welcome and syllabus module, you see right here, tables to print.
Oh, okay.
You'll find them right there.
Thank you.
Sure, no problem. You got the shapes table and the table, the periodic table.
Oh, okay. Well, it's great to see you today, Dr. Fred. I hope you enjoy the rest of your night.
All right, you too.
Bye.
All right, bye-bye. Any other questions? Yeah, all right. Well, thank you very much, guys. You have a good weekend. Bye-bye. Angie, you're okay?